An interesting thing to remember about our sense of touch and what we feel when we're judging the temperature of something is that we have to remember that when we touch an object, we are not feeling how hot or how cold that object is. We're feeling a differential in temperature. We're feeling a delta T. We feel a delta T between our fingertips and what we are teaching. It's a gradient of that heat flowing. So, for example, if I touch something like a desk, and I touch the wood on top of the desk, the wood um, feels maybe a little bit colder than my fingertips. Because my body heat is higher than the mean radiant temperature of the room, or the ambient temperature of the room, and that desktop is probably going to be the room temperature, maybe 21 degrees Celsius. So it feels a little bit colder. But if I touch, let's say the legs of that desk are steel, and I touch the steel legs, now those steel legs are sitting in that very same room, and that room is at 21 degrees Celsius. So those steel legs are going to be also at 21 degrees Celsius, but boy, do they ever feel cold. So those steel legs feel really, really cold. But what I'm feeling is actually the gradient of heat leaving me, because I'm more than 21 degrees. And the steel is going to conduct that energy out of me faster than the wood is going to conduct that energy out of me. It's a bit more insulative. The rate of change of amount of heat moving is going to be smaller in the wood than it will in the steel. So we're not feeling how hot or how cold something is. We're just feeling a gradient. So another example I put here is cookies in a frying pan. They're going to be the same temperature as a frying pan, but it's not going to burn you like the frying pan will, because that frying pan is going to pull that temperature out of you faster. So we're designed to feel the degree of heat, not the temperature. We are not good thermometers as people. And that is imperative to know when we're focusing on the comfort conditions and we're studying building science. So when you need to plan an environment or a building for comfort, you need to know about two different types of heat. We usually think of heat as sensible heat, but there's also latent heat that we need to know about. So when somebody says something is hot or something is cold, they're normally thinking about what we call sensitive heat, sensible heat. Sensible heat is actually the measure of how much heat is in something in terms of the excitation of those actual molecules. And every molecule has a material property, or sorry, every material has a material property that is called specific heat. And the specific heat tells you how much this sensible temperature is going to rise or fall, depending on how much sensible heat went into it, depending on the input of the sensible energy. So that specific heat of wood is not going to be as high as the specific heat of those steel legs. There are three different types of heat transfer. The heat is an energy. Energy is measured in joules, and that heat can move around. We can exploit the moving around of heat in various ways to do some very interesting and useful mechanical engineering applications. When we're exploiting the movement of heat energy, there are three major ways in which that heat energy can be moved. And that's radiation, convection, and conduction. Radiation is that it's that heat that can get transmitted, reflected, or absorbed to or out of something of mass. And remember, every material or every mass has a certain specific heat. So all bodies of mass, they emit a thermal radiation, and that thermal radiation is then either transmitted, reflected, or absorbed to another mass. The characteristics of how much radiation is going to be transmitted, reflected, or absorbed depend on the mass's initial temperature, its emissivity, and its transmissivity. And that's different from conduction. Conduction is spreading that heat energy, that sensible heat energy by direct contact of the material, in which case the specific heat of that material comes into play. But along with sensible heat is latent heat. So latent heat, when it's not detected in the conventional way that you think about measuring heat. You think about measuring heat with a thermometer. And that's sensible heat. If you add heat energy to something, you will see the degrees, the Kelvin go up, or the degrees Celsius or the degrees Fahrenheit go up when you add heat energy. You'll see it go down when you remove heat energy. You use a thermometer to tell you how hot or how cold it is outside. That's sensible heat. But equally as important is latent heat. We just don't measure it with our thermometers. But latent heat, heat is a form of energy, and latent heat is still an energy that gets used or moved when a substance changes its state of matter. So we could have something that was solid turn into a liquid. That's called fusion. Latent heat of fusion is liquid to solid, solid to liquid, the latent heat of fusion. Liquid to gas is vaporization. Latent heat of vaporization is the amount of energy that is used to turn from a liquid to a gas. And then solid to gas, if you want to skip, some materials can skip that phase. That's called sublimation, and that would be the latent heat of sublimation would be used to make that state of matter transition happen. So let's assume we have a gas and it liquefies. That's called condensation. The latent heat of condensation. And in this case, it's going to release that heat. It releases that latent heat. It's still an amount of joules. It's just not an amount of joules that would be measured on a thermometer. The most common example of latent heat is vaporization. Vaporization of water is a very common example. So you're going to fill a pot of water, you put it on your stove, you light the gas burner. The gas burner, of course, is putting joules of energy into that pot. What's going to happen to those joules of energy? Those joules of energy are going to be transferred into the water, and the water molecules are going to have a higher degree of excitation, raising its sensible heat. You could put a thermometer in that water, and the sensible heat is going to increase. You're going to see that it goes from your tap temperature, whatever that is, maybe 15 degrees Celsius, all the way up, and it'll climb. And once those molecules are really excited, it is going to, that liquid, if it's water, is going to reach 100 degrees Celsius. And your thermometer is not going to say 101, 102, 103, 104 as your water boils. Your water is going to start boiling. It's going to start vaporizing. The water in the pot is no longer going to be liquid anymore. Some of it is going to turn into gas. And you're going to see that rise up through your into the air. Well, as you're doing that, your thermometer is going to read 100, 100, 100, 100, 100, 100. But the curious question is, am I still applying buckets of heat, joules of heat? Remember, heat is measured as a quantity. Heat is a quantity of energy. Energy is just measured in joules. Heat is energy just like any other type of energy. potential energy, kinetic energy, etc. The quantity of joules of energy that you are putting in each second or each minute, however you want to measure, quantify your power, which is your heat delivered over time, it's still going in. The gas is still lit, right? So there must be heat energy being transferred into that fuel. It's not raising that sensible heat. I can't see it, but it is raising the energy. That energy is getting used to change the state from liquid to gas. So that's the most common example of this. Another example of it is gas liquefying, which is condensation. And in condensation, it's the opposite. It is releasing heat. So an example of this is, let's say you are in an environment that is sitting at maybe 3 degrees Celsius. And depending on the amount of humidity in the air, you have likely hit what's called a dew point. And what that means is that any air that has vapor or that has a humidity above a certain amount is going to condense at that temperature. So your breath, for example, you go outside on a crisp evening at 3 degrees Celsius, and the breath that you exhale, it was a gas, but it's going to condense when it hits that air because it has hit the dew point of that air. So you see that condensation as sort of steam coming out of your mouth. Think about the amount of energy that air in your mouth, your breath had when it was warm in your body versus the amount of energy it has when it's sitting outside of your body. It's going to have less energy. What did it lose that energy to? It released that energy in the form of latent heat in order to make the phase change as it liquefied and became condensed so that you could see it in the air. And we have a way of measuring this energy, but it's not just heat energy. So our word for the amount of energy that quantifies the excitation of those molecules is called enthalpy. And we can measure enthalpy of a substance as the sum of the sensible heat plus the latent heat that's happening. So that pot of boiling water still has sensible heat in it. It's still got a bucket of heat added to it from that gas burner. And then over time, you're adding more buckets of energy in order to keep producing that latent heat as you go through vaporization. We can measure the quantity of heat in joules. Joule is a standard SI unit for measuring heat. We shouldn't really ignore the fact that BTUs also exist and are still commonly used in many industries, including the HVAC industry. So a BTU is defined, one BTU is defined as the heat energy that would be required in order to take 1 pound of a certain substance, that substance being water, and raise it 1 degree Fahrenheit. And then BTUs per hour would be the power or the rate of that flow. But in the SI unit, we use joule, and joule is a measure of all energy. And if that joule were measured over time, specifically, if you want, that would be the power consumption or the power used. Specifically, if you measure it over a certain amount of time, being a second, then that would be defined as watts. Now, that's heat. That's heat. We just talked about heat. We did not talk about temperature. Heat is different than temperature.